Hey, folks. All right. So last week we, um, well, let's start before that. For this series, we've been working on a programming language. I guess it's not an example in here, but we've been working on a scheme-like programming language. Um, so if you're not familiar with scheme, this is kind of what it looks like. It uses S expressions, and in the inside of each S expressions are the things that are parenthesized. You've got an operator or a function as the first place, and then everything else to it is an argument. So 13 is the first argument, and the second argument is the result of this expression. So in the first stream, if we go into main.go, we worked on the Lexer. So the Lexer took the input program and broke it out into an array of individual components called tokens. And if we look at the Lex test, we'll see examples of that. So here, for example, we wanted this to be broken out into this. So this is the input right here. We wanted this to be broken out into this result of an array of tokens. So parentheses plus 13, 2, and ending parentheses. And then in the second part of this stream, last week, we worked on a parser. So this parser went from, let's look at line 64. The main function in parse took an array of tokens, and it produced an AST. So it went from this flat list of tokens that the Lexer produced, and parse itself produced an AST, which is a tree structure representing the real intent of the program. So what that means is that we've got broken down here by things like literals, which are plus, or actually in this, okay, yeah, literals are lists. So we broke it out into literals. That's things like plus or div or minus or numbers. And then the rest of them would be lists of other lists or literals. So it is defined, AST is defined recursively. Let's look at the definition up here. AST is a value, and a value is either a list or a literal. And as you can see here, this actually we could rename to AST. So an AST itself can contain a value or another AST. Oh, not here. The AST was defined as an array of values, so it would be here. All right, so now that we have this nested structure, we can interpret it. And that's kind of where the fun of building a language comes in. So you go from this unstructured string that the programmer types in, and you pull out the structure of it. The structure is the AST. And then once you've got the AST, you can execute it. So we're going to keep this we're going to keep this stream series pretty simple. Also, it's common that Lisps or scheme-like languages are dynamically typed. So the reason I bring that up is because if we were in a statically typed language, there might be an intermediate step here that was type checking. But in our language, we're not going to do that. We're just going to have everything type check during runtime. Yeah, so I guess we can clarify that static type checking. And there can also be other things that happen here, like constant propagation. Where if you have an expression like this, everything in there is a constant. So there's no need to evaluate that at runtime. You can evaluate it before runtime. So this could get transformed into this. But we're going to not do these. And we're going to get into evaluation. And even evaluation can be a complicated thing, or not complicated, but you have lots of choices for it. the simplest way to do evaluation is by just iterating over the recursive tree structure and evaluating things as you go and always returning a value back up the tree. That's called AST walking, and or AST, like directly interpreting off the AST, but most commonly I see it called AST walking. That's really easy. It's not the most efficient. It's just the easiest one. Other options for execution could be converting the AST to assembly, or converting the AST to Go, or to C, or to JavaScript. That's commonly called compilation. And another type of compilation we could do is where we compile it to a virtual machine that we make. And that would be a strategy that languages like Python take, or Java. They compile the AST to a bytecode for a virtual machine that they build themselves to. But for right now, let's just stick with the AST walking, because it's going to be really simple. And if we want to be able to do evaluation of this example project, what this is going to look like is that as we go, like, let's imagine this as a tree. We know it's a tree as a programmer. If we want to evaluate this, we have to go through steps where first we evaluate. If everything is a literal, then we don't need to evaluate it. But if anything is not a literal, we need to evaluate that first before we can evaluate anything outside. So in this case, plus is a literal, 13 is a literal, but this inner argument is not a literal, so we have to evaluate that one first. And when we do evaluate it, we're going to get 11. Now that we have this, we can evaluate this, and this is going to be 24. So this is what our AST Walker evaluation is going to look like, where we're always have to first evaluate any arguments who are not literals, like this, and then we can evaluate the argument. Then we can evaluate the current list itself. And we always need to produce a value. All right, so actually, let's copy this. And let's make a new file, AST Walker. And let's add, nope. Just add this as a comment because this is what we expect it to do. Okay. So AST walk is going to be defined recursively. It's going to do something like what we just said. If the value, well, okay, first off, AST was a list of values. So if we've got an AST, we need to iterate through the items in the AST. All right, let's. This is annoying. Let's start with a value instead of an AST, because again, we want everything to produce a value, and a list by itself at the top level of this program doesn't have a value. That is confusing, and I don't know how to explain that better right now, but hopefully you'll see it as we walk through this. So let's say that the AST walker takes this value instead. So here is where we can do if v.kind equals literal kind, literal value. Then we can return its value. Otherwise, if v.kind is a list kind, list value, then we need to grab the function v dot list 0 and its args, and call the function with the args and return that as the result. Why are you complaining? V.list. So these are not lists themselves. They're pointer to an array. So we dereference the pointer, and same here. This is a pointer to a token. Literal. How's that defined? Literal is a token. All right. And if we go into the definition of token, what we really want is its value. This. So literal, b.literal.value. And why are you complaining? Yeah, there we go. Because literal is a pointer to a token, and list is a pointer to an array of values. Okay. Why are you complaining? Oh, declared but not used. And function. Okay. So this, we're going to have to cast this as a function that takes something and returns something. And so as we can see in this example, when you have an S expression, you have to evaluate the operands first before you can evaluate the actual function itself. So you can't do the plus before you evaluate the 13, and the 13 is literal, so the result is 13, and before you evaluate this. And this is not a literal, so you have to go into it. So we could do that here, where, say, args is an array of anything, and for unevaluated arg range we have to evaluate all the args. Now we can pass the evaluated args to the function. The way that we do this, though, this is not going to work as we get. It can't be this simple when we get into complex things like control flow. So in the case of if, in Lisp, an if is commonly defined like this. So this is an exception. We said that you have to always evaluate the args first. Depending on the actual function being called, we're going to do different things. If it's a special function, like if, then we can't evaluate all the arguments, because then we'd always be evaluating everything in a conditional. And that's not what you want conditionals to do. You want conditionals to only evaluate this part if the test is true. Otherwise, you want it to evaluate this part. So this is kind of a there's kind of a dilemma here, which is that we evaluate args here. If so, special functions like if must be handled separately. So an example of that would be that we could do something like if function like we have special cases like this. Yep, and either choice is fine. It doesn't really matter. Let's do this. So also, we can't just cast here. What we have to do is that when we look up the function, we need to actually have a mapping of what the functions actually do. So we want to have a context object. We're going to need this anyway. String to any. Let's rename interface to any. And when we get to a function, we can't just cast it immediately. We have to look up what the actual value of that function is. So function. Just giving ourselves a couple examples here to work off of. Function name, function, the actual function we have to look up in something like the context. So here's where we could do the special. No, because Go requires all of these to have the same signature. Okay, let's handle. The reason that I'm getting uncertain about what we want to do here is because there's not just built-in functions like plus, there's also eventually going to be custom functions like define plus takes two arguments and adds them together. So let's do two things. One is if built-ins function name then let's handle built-ins separately. And for built-ins, let's pass them the unevaluated args. List, and we're going to skip the first one because that was the function name. Okay. Now let's give an example of built-ins. String to func. This takes a list of values and returns any. That's not height. And DK Barnes in chat asks, have I read Writing an Interpreter Go by Thorsten Ball or Crafting Interpreters by Bob Nystrom? Nope, I have not read those. I hear good things about them. I probably should read them sometime. I first started learning about compilers in a course in college before I dropped out, and have been like playing around with languages for a while since then. But no, I haven't read those. I hear that they're really good books for introduction to the topic, so I'm sure they're great. But no, I haven't read them. All right, so if is a special function, args are an array of values. So the if has specific components. It has this test. You can copy this out here. Test, which is the first argument, or yeah, first argument. Or condition. Then it has the then and else. I guess we can't name that. That Go doesn't want us to reuse built-in keywords. So we can evaluate this one, AST walk. And I just realized now that we need the context here. And the reason that we need context here is because if we had a variable that was defined like this, this would be inside of the context, and the if would need to have access to it. So we need to pass in the context for here as well. Now we can say if the condition is actually true, then we evaluate the then condition, otherwise, and we return it. Otherwise, we return else. All right, so this is a special case because, as I said a couple times already, it's a special case because the if needs to conditionally evaluate. That is not the same as what we want to do for plus and most functions, including all user-defined functions. Every single user-defined function um, needs to have its arguments evaluated before being passed into it. The way that Lisp and Scheme works around that is macros. We're not going to do macros here, but when you have macros, they don't get the evaluated arguments. They get all the arguments as an AST, and it decides whether to evaluate them. And it can even, or actually, I don't even know if it decides whether to evaluate them. It needs to return a new AST in the case of macros. But we're not going to do that right now, and I don't know if we'll ever do that. I did do it once before in a scheme that I wrote a long time ago, but it's tedious, so I don't know if I want to get into that. Okay, so here we define the if built-in function, and well, let's just do plus as well. This one, all of its arguments need to be evaluated. Actually, but they don't have to be evaluated up front. We can just start accumulating. int. Yep, it needs to take context again. Yep, and then we'll pass this to an int because all these AST walk functions, they return the empty interface, which is nothing. It needs to be casted before you can do anything with it. Even this might need to be casted. All right, so because we've defined plus as this special built-in function, it needs to evaluate all its arguments and return that accumulated result. And we can copy that to implement minus as well. So instead of plus equals, we do minus equals here, but everything else stays the same. Just clarifying that this is for later. And clarifying that this is an example of evaluation. Okay, so I think we handled enough cases right now that we can even skip all this part. Because this was for things that are not built in. So if we comment this region, we need to return from here. We should have enough that we can interpret this basic example because the only things that we called in here were plus and minus, and we already defined plus and minus. But I feel like I'm missing a return. I guess we don't even need to check here because there are only two conditions. Okay, so if something else, let's panic instead. Because we don't support anything else, this is basically the case here is that we're calling something that is not built in. For example, if the user typed in this, we would get here because 3 is not a built-in function. All right. That seems so far like it would work. So we can comment this. And let's try building. Mix named and unnamed parameters. Okay, yep. We don't need to name any of them. It's fine. Built-in initialization loop for built-in. What does that mean? Built-in refers to AST walk refers to built-ins. Interesting. What? That's really interesting. Okay. I guess we can't declare this outside Lexer. I've never tried to do this in Go before, so I didn't realize that it would have an issue with this. I guess their issue is that we're trying to call AST walk in here, but I'm also trying to declare built-ins statically, and AST walk itself calls built-ins here. So I think let's, rather than calling built-ins as a global, let's pass it in here. That's annoying. All right, let's just initialize these separately. Initialize if, initialize plus, and initialize minus. And if this weren't Go, we could do macros or something to make these a little bit simpler, because the only thing that changed here was this. But Go likes copy and paste, so that's fine. And now in main.go, we have to do the initialization. Initialize built-ins. And I forgot that we needed a context. Right. So we didn't want... okay, yeah, we still have to figure out about this. I'm not sure yet if we have to pass... Oh, wait, do we have to pass in a list, or do we have to pass in the outer thing? Let's print out what this is. When we get to there, it looks like we still have compiling issues. Let's build this again. Any type is not an expression. Okay. Undefined value context. Yep, that's here. CTX map string any. And oh, those already have it. Now line 56. Built-ins function name. Okay, yeah, we probably need to cast this to a string. Oh, okay. All right. We can't just do casting here. We really should be doing evaluation. An example of why we should be doing evaluation is, yeah, I guess we can assert that it's a token for net, or that it's a literal. I'm trying to think if there is a good reason that we'd want to not assume that this is going to be a token. Let's just assume it's a token. So it's a literal token. And we need to get its value, which is the string. All right. Now line 57, an array of values map string any. Right. It's context that should have been passed in. Yep, it was passed in. Line 46. Oh, great, it built. All right. So I think in main, we printed out the AST. Okay, we're already printing it out here too, so that's fine. Yeah, that's fine. I'm not really sure what this AST walk is going to do, because I don't really know what this indexing is here. We inside the AST walk function, we said that we wanted a single value, and that made sense in my head, but it's not connected to what parsing actually returns. So let's see what happens. All right, that printed out too much stuff. That's kind of annoying. Let's just hide printing the tokens out for now. And where is this panic? Who is panicking? Oh, built-ins. Yeah. Let's do, that instead. We just need to initialize the actual built-ins map. Okay. That printed out stuff, but I can't see what that. Why is there a plus at the end? Is it printing out this? Why is there no? Oh, we didn't do new line. Print new line there. Okay. So the first line we printed out the AST. The second line we printed out plus. So the result of this AST walking was plus. That doesn't really help me. What's this first one that we passed in here? That doesn't help me either. Let's pretty print it. Okay, all we passed in there was plus. That's not what we want. We want to pass in this entire thing. But AST walk. If AST walk needs to take an array of values, all right, I guess it has to do this. And this case will no longer exist. And we can switch out this v.list for AST. Now, how do we handle that case of evaluating a single literal value? Well, let's see. The compiler is going to fail now. Let's see what happens. Line 10, AST walk. So here we do need to evaluate a single value. Let's build a new function then that can handle either. I don't know what to call this yet. The value context px map. Any returns any. If it's a literal, we return the literal token's value. Otherwise, we call AST walk with the list. All right. And everywhere that we called AST walk before, or most of the places, we need to call this AST walk 2. And this is just a really bad name while I haven't yet figured out what we're doing. All right. Let's see why this is panicking. Line 24. I think what this is going to end up panicking is because here, we returned token values. Token values are strings, but our program wants to be dealing with numbers. And nowhere did we actually do a conversion between token strings and numbers. So I think actually we need to get more complicated here. We need to switch v.literals kind. And if it is an integer token, we need to do parse int, basically, and I can't remember. It's something string convert. I have to look it up. String convert parse int golang. Parse int. This is the actual token. So let's bring that out. Token's value here. If error not equal nil, we'll just do this terrible panic idea. And these are packages that we need to add. All right, so once we've converted it, we can return that I, but I think parse int returns, all right, it returns an int 64, and so far in this program, we were doing int. So that, I don't think that conversion is going to work. We need to convert to int 64. But that's going to be annoying for subtraction because, oh wait, no, that's fine. Int 64 is not unsigned, it's signed. Okay. That's a fine choice for now. And what I was thinking about there was that if it were uint 64, then the problem would be if we did, like, if we wanted to do negative numbers, then that would not work. All right, so we handled the int 64 case, parse int, but there are other kinds of tokens. Case identifier token, I think. Go back to Lex, syntax token, integer token, identifier token. So the only kinds of tokens that should be in here. The syntax token is not one that you can evaluate. You can't evaluate a parentheses like this. These get evaluated as a list. In fact, by the AST stage, there are no parentheses anymore. They disappear, and that just becomes part of the structure of the program. And then, so integer token and identifier token. Identifier token can just be returned just the value, because this is the case of like plus, and this case is case of like 12, 1. All right, build and run. Now, is this the result that we expected? I don't even know. 12 minus 1. Let's put this into Python. I can't believe I need to go to Python to do that. 23. We got 0. Those things don't line up. So let's figure out what's going on. Let's first try printing here. Let's see what happens. Print line, just parse and integer. Okay, that looks good. So here, so far here, we're all right. Now let's try plus and minus. Also, let's make this program simpler. Oh, these are still part. That's not good. Let's just make an addition program. And a subtraction program. And let's try the addition program. That looks good. that does not look good. I think that we're applying the evaluation. Oh, okay. All right. Here's the problem with subtraction. It can't start at 0. This starts at 0. We need to start with the first argument. And then here we skip the first argument. Why are you complaining? Hard declared but not used. What's the issue here? Oh, yeah, didn't declare it. All right. Build it. Okay, that looks good. Let's try the more complicated example. 24. That is what we expected. All right, awesome. So we still have a little bit of time. So let's do user-defined functions. So this is the syntax for defining user-defined function. This means that define is going to be a new type of built-in. Value, context, map, string, any. And the important thing in define is that it's going to add a new function to the context. And actually, define. Let's change this from define to func. Because it would also be nice to have something like this. Let's start with that. The var one gets complicated. This gets well. Actually, both of these get complicated. So in addition to, we can't just define these user-defined functions, because the point of a user-defined function is that you have to be able to use it afterward, and our AST Walker doesn't support the idea of using afterward. We only went through one line right now. So that's just going to be something we keep in mind once we add support for this. So defining a function is going to define a new inner function that takes args sorry, this is not what its name should be. Function name. The function name is going to be the first argument. And we're just going to assert that it has to be a literal. So that's the function name. And inside of here, the parameters are going to be the second argument. So inside of here, we have to modify the context and add the parameters mapped in. So let's take this plus example. So the function name would be plus, which is this first argument in here. The parameter list would be that second argument up here, the A and B. And then inside, once this function gets called, we're going to have to modify the context inside of this function and map this example here. A has to be 1, and B has to be 2. And one more piece of complexity is that we don't actually want to modify the outer context. We need to copy this context. And we need to only modify we need to only modify the context inside of the child, inside of this function, because we don't. If you have a function like this plus, you only want a and b to be defined as 1 and 2 inside of the body of the function. So you need to make a copy of this context because it should only get mapped inside of the body of the function. You don't want a and b to be 1 and 2 outside of this function. If there was if there was already this defined out here, and you did this, you don't want a to be 2, which would happen if you did not make a copy of the context right here. All right, so we'll need to implement this copy context function, and not 1 or 2. It should be the result of walking the first argument and walking the second argument. And it should not be a or b. It should be params 0 dot literal dot value. And we can't even hard code how many there are, because there can be different numbers. Like this would be fine. This would be fine. So we can't just hard code these. We have to loop through all of the parameters. Okay. Now what? And yeah, here this should be I. And this also needs con. Whether or not you pass child context here or context, I'm not sure if that matters. I don't think it matters because you don't. Yeah, I don't think that matters. Why are you complaining, params? What's the issue? Oh, yeah. I'm doing this because, just like right here, we require that the parameters to be a list of parameters. All right, and the only thing I think that's complaining here is copy context. So copy context, let's define that. Let's get this. Oh, no, that's not the same one. This one. Yeah, all right, never mind. This one's simpler. Maybe in newer Go there's a shortcut for this, but if there is, I don't know. Eval range in out val range out. All right. Let's build it, and we're 67. Okay. In here, okay. So I got too eager. This is where we defined a user function. We added the user function's name to the context, and we started defining this new function that would handle how it actually gets evaluated. All we did here was do parameter binding. Now we need to actually call the contents of the function. So this is going to be AST. All right, how do we do this? Definitely going to return whatever we evaluate here. But in this example, what we need to evaluate is this part. All right, and that is actually, we can define that out here. args2 Yep, so the second argument here to this function is the body of the function. So this is a little bit simpler. We need to evaluate the body with the child context. All right. And one more thing I realized, which is that we add identifiers to context here, but nowhere do we look up identifiers other than functions. And actually, we don't even look up functions. Yeah, that needs to happen here. So now we need to implement this. This should no longer panic. So we can uncomment some of this stuff. Let's see. This is going to return any, so we can cast this from any to our function signature. We evaluate the arguments, that's fine. We need to pass in context when we do this. Okay, that looks fine. The other thing, yeah, identifier token. So here, we can't just, the thing is that plus or if, these are built-ins. Those we'll need to handle separately, but if we did something like that, var and we want to refer to A, we do actually need to look up all identifiers in context. Now, that means that we need to change the way that built-ins are done, I think. Or does that not fall into this case? Let's see. Let's try all these programs. Add still works correctly. Minus works correctly. The example works correctly. Let's try a func example. Plus AB plus AB. So we want to evaluate this line first and then this line. That itself is going to be a problem because we don't have a concept of evaluating multiple lines. But let's see what happens. Build. I think that nothing is going to happen. Okay, nothing didn't happen. Panic. Where did you panic? AST Walker. Use. Interesting. Okay. All right. So the thing that's panic on is that this is kind of nonsense. Or maybe that's nonsense. Let's print out what it's seeing. Let's print out all the args. And we need to print it out before it panics. And let's get some more indication. All right. So plus this, yeah, this does not make sense. These things are not connected. That's really weird. But something else that we need to now deal with is that when you have multiple of these right next to each other, we need to be able to handle multiple statements after each other. And the way that it's common to do it in Lisps or schemes is to wrap everything inside of a begin block. So begin is another special function that evaluates all the statements inside of it and returns the result of the last function that it evaluates. AST block arg context. And in addition to supporting this begin in here, the trick that we do is that when we get back an AST, we wrap the AST itself in a begin block. So we say the AST equals AST token value in kind identifier token, and yeah, these are not an array of tokens, they're an array of values, so we need to wrap this first. Kind is a literal value. Literal is, yep. And the second one is the actual AST itself. And why are you complaining here? Oh yeah, let's not. All right, we reuse the name and Go doesn't like that. We reuse the name of the type. All right, let's try this. And that looks like it. Infinite recursion. Where'd you go? Stack Overflow. Inside of parse. Oh, but it's during the pretty printer. I saw that in the trace somewhere. Yeah, right here. All right. Why are you doing infinite recursion? Let's try making a copy of this and taking the address of the copy. Let's see if that solves this for us. Yep, it did. All right. Now what's the issue? We're still having that old issue here. And I'm still confused by this because these parentheses don't even match. Like, that has an ending parentheses. Yeah, this is confusing. It might be parsing this incorrectly. This one looks correct, but yeah, I'm not sure why this is doing this. Where do we go? I want to see if we get to the begin block ever. Okay, we do get into the begin block. Let's print out each individual AST that we see inside of the begin block. We only see one. Okay, well, it panics. Okay, that's fine. Okay, the parser is wrong here then. It should have ended right here. That should be the complete AST. It should not include all of this. So this is actually a parsing issue. And let's get rid of this. What I'm more surprised that it actually parsed everything than that. Where's this example? I thought that most likely it was going to only parse this, and it was going to not even see this at all. So I'm really surprised that it parsed everything plus a lot of extra ending parentheses. Let's print out the tokens it saw. Ah, that is okay. These are quite wrong. These should be completely separate tokens. So not only do we have a parse error, we have lexing error. And the issue is inside of here. So we need to be okay. So we only checked if there was a space between stuff before, but we need to check not only if there's a space, but if this is closing parentheses. I don't think that there's a case where it can be an opening parentheses. Okay. That did not fix it. I need, yeah, need to get the logic right there. All right, now we've got, okay, awesome. Whoa. So it didn't really turn out to be a parsing problem. It turned out to be a lexing problem once we've got the Lexer correct. Now it did what I expected. So let's get rid of some of this stuff so I can show you. So now begin only sees the first one. That's what I expected. I expected it not to parse the rest of it. So to parse the rest of it, we need to put the parser in a loop. And keep on parsing until we get to the end of the file. For parse index less than, well, not to the end of the file, but to the end of to the last token. Parse index. Child the next index. All right. And set the parse index equal to the next index and pass in parse index here. Why are you complaining? There. Okay, so need to keep parsing until end of all tokens. Now we see plus inside here, and this does panic before we get to about yeah, panic before we get to evaluating this plus 2. But this is all right. So we're parsing everything in here correctly. We've got the begin, then we've got the func plus, then we've got the actual call of plus. Now let's see what this is complaining about. Let's run it down here, and let's pull this up here. 12. Okay, that is wrong. Yeah, probably because we want context as well. Yeah, that's what it's saying. It wants this list of values, not just this list of. And there's also this discrepancy. It wanted a value, and we passed it in any. So I think actually this is wrong. We need to pass in any here, and we don't need to do an interpretation here because this will already have happened. And what's the complaint? 121. All right, what happens now? So this is just one more thing. We printed out this. It fully evaluated this function definition spot, and now we got into evaluating this. So that's great. Where are we panicking? Line 81. Okay, cool. So the issue is that in this example, we actually made a programming error here. If len prems not equal len args, expected args to Yep. So our function itself is wrong. We go to this plus 3. Okay. Yeah, so we got 5 like we expected. So this was a long and potentially confusing session. So let's just walk back through everything that we did. To do evaluation of this language, we decided to do a AST walking interpreter. And when you walk an AST, you have to go through each statement in the top of a function. You have to, so the basic file that you want to see is something like this. And it can have multiple statements inside here. And we expect that only the all expressions get evaluated. Only the last one is returned. That file transformed into this before the AST walk stage. That way we can define begin as the function that iterates through each statement in the file, each expression, and runs them, and then returns the result of the last one. So inside of this AST walk, first thing we do is look up the function. At the top level, we expect that all the functions are... Oh, no, it's not even about the top level. First, we check if the function is built in. If it's built in, we hand off to the built-in functions definition. Otherwise, if it is a user-defined function, then we look up that user-defined function in context, which is something that we populate throughout the process of evaluating the program. We evaluate the arguments, and then we pass the arguments to that user-defined function. Let's rename this. But evaluating functions is only half of evaluation. The other half is evaluating literals. So we have this other wrapper function that takes a value if the value is a literal. If it's an integer, we convert from the token's string value, like the string 1 or 12, into the number 12 or number 1. And if it's an identifier, we look up the identifier in context and return it. And just to show an example, this is if we defined A to be free, and if we had this expression plus A1, we'd expect the result to be 4. The definition of something like func is a little bit more complicated because we have to create a new function from the specifications of the user, and we assign that to context so that later on, when it's called, they'll get this function and be able to call it. And because this function is a closure that closes over stuff like the body, which in this example is this right here, when you define a function, you give it the name, the parameters, and the function body. It's able to map the arguments that the function is called with, like 1 and 2, to the parameters where the function is defined, like A and B. And it's able to interpret the body, which is this right here. Yeah, so this is, we can just keep on going from here. This can't do very much control flow, so it can't do recursion yet, or if we did do recursion, we would only be able to do infinite recursion because, oh, okay, we did implement if. Well, we implemented if, but we didn't implement Boolean logical operators like less than, equal to. So in another session, we can get into implementing equality, implementing less than, greater than, but it's basically going to look just like these. And once we do have that, we're going to be able to implement Fibonacci functions, for example. If A less than 1, A otherwise fib, and we would almost be able to do that right now, but we haven't implemented this. Yeah, so I'm going to leave it at that right now. Thanks, everyone, for listening in. And I haven't decided yet what we'll do in the next stream, but possibly we can talk about compiling, instead of doing an AST interpreter, maybe we can talk about compiling this to Go as just an alternate backend and way of evaluation. All right, thanks, everyone. Until next time.